Welcome to a tour of recent experimental design free response questions. Uh, Experimental design questions are present on all of our AP Physics tests, so in some way they're rather predictable. On the other hand, they vary quite a bit from year to year, and so we want to actually see a cross section of what you might run into, and look for there's a rather high level kind of set of common things that we could look for, but they're all different from each other individually. So let's get going. So, in looking at these, I'd like you to be able to see them yourself, and we'll in fact ask you to pause the video and go through some of these. So, you'll need to have access to them. These are questions from 2023 and 22, 21, and so you can get them either by using our link to the AP site of released questions that's in the Schoology FRQ exercises folder, or if you simply pull up this slide presentation, which should be linked from the syllabus, and there's links in the presentation so you could follow along and use some of those links, whichever one works for you. But I will ask you to please look for yourself, because I think that will give you more valuable information, make it more likely to stick. In all of these, even though they're quite different from each other, we can help ourselves by determining what type of purpose the experimental we're being asked to address, and what are the key variables that we're going to need to calculate or measure in order to answer that question. And everything we do should funnel through those guiding questions, and it'll help us really focus in some pretty broad questions. Okay, so first up, 2023 FRQ number 2. If you can navigate to that and get a good look at it, and I haven't said this, or if you haven't heard it previously, this is the most valuable advice. When you encounter a new free response question, read all the way through from beginning to end before you start answering any part of it. So take about 5 minutes, pause the video, and open up the question and read all the way through and start thinking about what your big picture plan would be. So go ahead and do that. Okay, you are back and ready to discuss this. Hopefully you have some opinions about it. Maybe you're looking at it. Maybe you've got the beginnings of how you're going to approach it. So this one was kind of a classic. It's the one that physics teachers are trained to expect for experimental design. And that said, it's pretty challenging, I think. So they give you a data set, and they want you to explain how you would use this data in order to determine a constant. And in fact, our type of purpose that we have, we are going to determine an unknown constant. And if we think like we're filling out a lab planning template, that's a useful mindset to be in. And when we're determining an unknown constant, one of the things I hope we've learned is that you don't actually set out to just measure the constant, you measure variables that are attached to it. So we'd look for an equation if we want to find acceleration that has acceleration in it. And there is an equation that has position, time, and acceleration in it. There is an equation, that has v final and time in it. So that's a possibility too. There are some other valid combinations too. There's a number of good ways to approach this. So you had, like I said, you had to come up with that plan, but they did specify that they want a linear graph, and that we would use the slope. Slopes tell us constants. So we want a linear graph. We want to be able to use the slope. So one way to do that would be to calculate the V final values for each of the positions and times. You could calculate what the V final was at that point. In other words, the instantaneous velocity. Because the V original was 0, then this original main equation could go into a planning template that would put V final on the y-axis, time on the x, and slope. The acceleration would just be the slope. To me, the one that jumps out a little more, I think is almost a little easier to approach, is if we use our displacement equals VOT plus 1/2 AT squared. Again, with VO being 0, that simplifies to displacement on the y-axis, time squared on the x-axis, and 1/2 A for the slope. In all cases, we would need to do some kind of modification of the numbers. If we were to graph them raw, we won't get a straight line. If we calculate the V final or calculate T squared and graph those, we can get a straight line, and the slope could then be used to calculate acceleration. As far as the points go, 1 point was given for coming up with a plan that would produce a linear data set and would tell us acceleration. 3 points went into the graphing itself. So setting a good scale, plotting the points, putting a line of best fit. 2 points for accurately determining that slope and using it to come up with acceleration. The way you come up with acceleration does vary depending on what your plan was. And then the follow-up on that was explaining how you could calculate G from that experimental acceleration. And you'd have to tell them to, give the angle of the ramp or something similar to that, and show how you could then calculate that G using your acceleration and the additional measurements from acceleration down the ramp being G sine theta. Okay, so that's the super quick rundown. There's were a lot of ways, though, to earn credit, even if we didn't get it perfect. A lot of people maybe look at these and say, those aren't the variables that I came up with. Maybe I just had position and time, and I figured that slope of a velocity, and I just said position over time is velocity. Well, we need to be mindful when we do that, that the velocity we were calculating wasn't V final. It wasn't quite accurate to put those just plain distance over time with each time. But you would get a graph. And if you followed through on that plan and you did a good job with your graph, you could still earn 7 of the 8 points, even if we had a not perfect plan, a not valid plan for the linearization. They were looking for you to demonstrate your lab skills, and as long as you did follow through, you could still earn those. So it's important to remember that displaying these skills is valuable, independent of the analysis plan that you come up with. One mistake doesn't have to sink your whole score. Okay, so hopefully that takes a little bit of pressure off. Let's look at another FRQ that is quite different. So I'll ask you to check out the 2022 and do the same thing. Read all the way through and start to formulate what your big plan might be, and then come back in a minute. Okay, so if you've unpaused the video, let's go ahead and in this question, we had to come up a lot more with the procedure, and the purpose that we were serving to address with this was checking whether our two variables are equal. And those two variables, the key variables, were the gravitational potential for the block and the block's kinetic energy. So we should focus on those. Our measurements should be aimed at making sure that they will produce these values. So there's 7 points for coming up with a procedure that would lead to those PE and KE values. And we can't measure energy directly, so we have to measure stuff like M, G, H, kinetic energy with m and the speed, and they'd want the speed right before it hit the ground. And there's lots of good ways to do that, lots of good ways to measure. So you could come up with a procedure for that, and tell what the equipment you would need, describe the calculations, and what you would do to reduce error. And so I'll go ahead and throw out there right now, I should have mentioned it sooner. For reducing error, always recommend applying more trials, taking more steps. Good science will always seek to have more data to use, based on more trials, so that we know there wasn't just an error in one of the trials throwing off our results. Now, if we read all the way through, we see hints that when the students thought the PE and the KE for the block should equal each other, that they're not correct. They were forgetting the kinetic energy of the wheel itself. Please note that in the procedure part of this, you were not asked to fix that. It wasn't your job, even if you could see that right away. It wasn't your job to change the experiment, to change their hypothesis effectively. You would just do something to collect the PE and KE data, and if we did a good job, like we see some data here, we can see that the change in gravitational PE is not the same as the change in the kinetic. And so we can see that the student's hypothesis was incorrect. That is a good experiment that led to that valid result. But now they want you to explain what happened and fill in the missing information. That missing information was the energy for the spinning wheel, and we would want the total energy gained at the end if we lost 0.4 joules, that our block energy plus the additional amount for the wheel energy, that together those values would add up to 0.4 then. We also have some data that is aimed specifically at the kinetic energy of the spinning wheel. So they give you this graph, and they're showing you, they're basically very transparent in what you would need to do for the linearization. And so you just have to be able to catch up with the plan that they had. Well, if I take my 1/2 I omega squared equation, put that into an equation template, this plan is if kinetic is on the y and omega squared is on the x, that my slope should be equal to 1/2 I. So that's what you do. You draw in your straight line. You calculate the slope based on, excuse me, points on that line. Do not use the dots that they provided. Instead, look for good spots to measure and get accurate coordinates. Calculate your slope, and then my slope here should equal 1/2 I. And so that should allow you to calculate I from that slope. Okay, moving on to the next one. Get a look at the 2021 question and then come back. Okay, so this one, still quite different than our previous ones. Has a little bit of a mixture of procedure versus analysis, but also has almost no existing equations. So this is a very interesting one. Couple characteristics. This question can seem pretty open-ended if all you do is read the first page, and you might find yourself panicking. But if you read all the way through the problem, they hand you a data set, which tells you your two key variables to focus on: force and radius of our plastic rod. And they even just have a graphing exercise. I will say, if this whole question is overwhelming to somebody, they may want to choose to start out simply by doing the graphing part, which does not require any planning on your part. You just need to set the scale and do it. So I'll talk a little more about that when we get to it. Our overall purpose here was determine the equation relating to variables, because really the question is whether F has a direct linear relationship with R, or turns out it might be direct quadratic. And that's the question: direct linear or direct quadratic. So to me, that's finding the equation. Even if we're not going to complete the equation, we're getting the beginning of that relationship. Okay, so we have a few procedure points in the beginning for describing what you would measure and how you would measure it, with that focus on we want to get values for braking force and for radius. Well, diameter of a rod is easy to measure, and then we would calculate radius just by dividing that by 2. Notice that they call for repeating each trial so that we can reduce our error. You always want to be in favor of more trials. And we vary our values so that we can get a range of values to graph. But that's only 4 points. The other points will come down to analysis. So to me, these are the hardest 4 points in this question. And so stick with me. Look at what we have. If student A is proposing that force as a variable relates to R, direct linear, and that would be the beginnings of the template then. That's what we'd fill in, and that should produce a straight line graph. Student B calls for it to be the area, the cross-sectional area. Well, because this is circular, that area would be pi r squared. And so really the area variable boils down to relating to r squared. So if I substitute the pi r squared and look at where my template ends up, that pi would go in with the constants. It would be part of the slope if I were to linearize it. However, they don't have us linearized. They want us to understand it's between f and r linear or f and r squared quadratic. And we should show what those two trend lines would look like if we graphed the data raw. I would not blame most students for looking at this and being a little uncertain exactly what they want to get out of it, which is why having the next section is so valuable, and knowing that it's there, because they handed us a data set and gave us a blank graph to plot it on. So I sit down, I set my scale to fit this data set, I plot my points, I recognize that this seems to be curving upwards, and so assume that it's going to be a quadratic. Again, if I don't know where to start, having a straightforward graphing task with no planning being asked for, this would actually be my starting point, because then it makes it a lot easier to figure out what they're asking for here, which is essentially they're asking you to say that you understand you should look for a straight line or a quadratic, and that will answer the question that which trend you have. Clearly we have a quadratic, and you're expected to then show that you understand that that's significant for student B's hypothesis. Okay, moving on again. Last one in our sequence, and this one is an odd duck. So, 2019 FRQ number 3, take a look at it, and then we'll discuss. So we have a spring launcher, and they're telling us to find an unknown constant again, and there's 2 equations that go to this k. F equals kx, or spring potential equals 1/2 kx squared. But then they very clearly specify they want us to launch this ball, launch the sphere using the launcher, in which the student uses the launcher. And so we must launch the sphere, and taking force measurements with that would be very difficult, because our force is not constant when you launch that. It's going to be much easier to use energy. And when I understand that they want me to compare the spring energy to the launch energy, well, then I have my variables. Spring energy, energy after the launch, we'll use those to lead us to our unknown constant of k. So why did I say have 2 purposes? Well, clearly they want us to come up with a way of finding k, but we're also testing whether k is constant. So determining equation relating 2 variables, that is checking out the type of equation. whether it's linear or if k isn't constant, it won't be linear. Okay, so here's an example. There's some to choose from, and I haven't mentioned yet going to look at the sample responses and scoring guidelines. Hopefully, you already have started doing that for some of yours. This is a very valuable thing to do whenever you're reviewing your FRQs. So, in the scoring guidelines, they provided an example procedure here. This is one way to do it. There were several good ways. But all of those really came down to comparing spring energy and energy after the launch. In this one, it was kinetic energy, which we obtained by getting the instantaneous velocity. We could use a motion sensor, I will also point out, for instantaneous velocities. Video camera and analysis software is a very easy tool to use to get instantaneous velocity, the velocity right before the block hits the ground, or in this case, right as the ball leaves the launcher. Okay, so first 8 points in that problem go to identifying that key idea, conservation of energy, and linking that to some variables you can measure, and then describing how you'll take those measurements and what calculations you'll do. For testing whether k is constant, if we graph the values for that we can come up with using an equation, and we'll see if we get a straight line. So we can't actually calculate the spring energy, and we will have to instead link. So we actually have here 1/2 kx squared and 1/2 mv squared. If we link these and put our variables in, x and velocity, for the variables in our previous one, we can compare x squared and v squared and graph that. And if we get a straight line, then k is constant. I will also mention that if you are, anytime you want to produce a graph that has a straight line, the test that we then do is apply a linear regression. So this is always a good idea. If we expect a straight line and we draw a line of best fit, the best way to make use of that is to do a linear regression. You don't have to demonstrate knowing how to do it. You just need to know that linear regression is a good idea. What about our last part here, where they changed up the variables? The final 2 points, they changed the variable from being x and v to x versus m, kinetic the spring energy, and the mass of the ball is going to mess with us there. So if we graph that launch speed versus the mass, and they showed for a sample calculation for taking our equation, assuming k is constant, solve for v, and we can see that v relates to inversely to mass. Mass ends up in the denominator, and so we would expect an inverse graph. Yes, it's an inverse square root, but basically this is always the general shape for that kind of inverse relationship. So they're asking you to show that you understand that when they ask you to sketch that graph. Okay, so some takeaways. Always read through the whole problem before you get started. Give yourself time. This is why I like to encourage people to do the experimental design first. So take the time to get it right. If that means you go work on some other stuff and let your brain process it a little longer, you'll have 90 minutes. So go ahead and do that. If you, again, think about filling it in the way that you would a lab planning template, if it feels like you're doing that and feels like you're onto it, then you are going in the right path. So relax. You'll do great. Can't wait to see what you can accomplish. Good luck.